Okay, so countable and uncountable sets. Very basic concept, but very confusing. And before we start this, I want you to get familiarized with this thing. See, like suppose 2.14763. Okay, yeah. Then suppose 2.147147147. Okay, so what I just listed are two kinds of numbers. This one is called terminating, and this one is called non terminating repeating. This is not a standard form. I'm just saving time. Okay, terminating. Okay, it terminates. If you remember, this is a rational number of the form p over q, where q is of the form 2 raised to the power, say, t, 5 raised to the power r. Okay, so t and r belong to the set of positive integers. Okay, I could have written, okay, they can be 0 or any natural number, right? Union 0. And I need to write straight. Anyway, okay, so these are terminating, like a number of the form, and obviously P and Q should be co-prime. Okay, so suppose if I write 76237 over like 1 or 250. Okay, so this is a composite number made exclusively of the factors of 2 and 5, right? And just 1 2, and I guess 5 5 25. Yeah, 3 5s and 1 2. Okay, I think this is pretty basic. Anyway, non-terminating, but this is very crucial to understand what we are going to understand. Okay, so if you already know this concept, just skip a few seconds. Anyway, so this is non-terminating repeating. Okay, so this 147 keeps on repeating. So if it has any factor apart from 2 and 5, 2 or 5, no, 2 and 5, right? It can have 2, it can have 5, it cannot have any other thing, the denominator. Okay, so that will be a non-terminating but repeating decimal, and that will still be a rational number. Okay, now our interest is in the numbers which are of the form 3 point, okay, I don't know the exact expansion. I'll just write a random number, okay? 2.10100100001 this. So we can clearly observe a pattern: single, two zeros, three zeros, four zeros. This will keep on increasing. This decimal is never going to terminate, and it is never going to end. Okay, terminate, that is the same thing. It is never going to repeat itself, right? A portion will never get repeated. It will just keep on increasing and increasing these number of zeros. So it is a non-terminating, non-repeating real number, and these are what are called irrationals, right? So these are the irrationals. Point to be noted is that irrationals cannot be expressed in the form of P over Q, and this thing will get a little more clear in a while. Okay, so let's look at this now. Yeah. See, so what about the concept of countability and uncountability? Okay. Countable, this word comes exclusively from the set of natural numbers. Okay. What is the set of natural numbers? It is just 1, 2, 3, 4, 5, so on. Keeps on going. Okay. No matter how far you go, you will always have a number in this set. It's not like you will exhaust all the natural numbers. Like if you start counting the stars in the sky, okay, let's say here are the stars, okay. You start counting the stars. So you counted first star, then second, then third, then fourth. We know that stars are infinite, right? Will there ever come a point when you will have no natural number left to assign a number to the stars you are counting? A lakh, crores, millions, trillions, anything. You can think of anything. Like if you are able to count the entire stars, you will always be able to count, right? You will always have one number in the set of natural numbers which you can assign to your next star in the counting, right? So this is called countability. It is exclusively related to the set of natural numbers. It has everything to do with the set of natural numbers, okay? So countability actually means that for a set containing elements, okay, containing elements, we are able to assign a natural number to all the elements of that set. This is what countability is all about. And in more precise terms, when we are able to map every element of a set with a natural number, then that set is called countable. Okay, I hope this is pretty straightforward. Now let's see the sets that we have with us. Okay, so let's take the set of integers. Okay, so integers I'll write like a very standard example. Integers 0, 1, -1, 2, -2, 3, -3. It is formed of, yeah, it constitutes of natural numbers only, right? One extra, and then natural number with alternate signs, like the way we have written it. Okay, obviously not the right way, because there is something called order in a set. But the point is not the order. The point is that whether or not we are able to map all the elements of this set to a natural number. And the answer is, of course, we can. Anything made up of natural numbers will obviously, okay, no, maybe not a precise statement to make, but okay, you get the idea, right? We can do this mapping till infinity. Okay, we can go, keep on going in both of these sets, and we will still have something here which we will be able to map to the number we get here, right? So the set of integers is countable. Infinite, obviously, but countable. Okay. Now let's take the next set. Let's take the set of, wait, yeah, the set of rational numbers. What is a rational number again? Any number of the form p over q, where q is not equal to 0. Okay, because, yeah, I hope no one has any confusion in this. Okay, I have this idea that I would like to, okay, let's say let's say 17 by 2, right? What I can do is I can write 2 times 8 plus 1 is 17, right? Euclid's division algorithm. Okay, so this is our x. But wait, I'll write it as 8.5, right? So I found an x. Now what if instead of 2 I have 0 and here I have 17? Is there any solution to this equation? Is there any value of x that can give us 17? No. That is why this is not defined. Division by 0. I don't know why I explained it, okay? Anyway, so this is our set of rational numbers. Now, what are rational numbers made of? P over Q, where P and Q are coprime and P and Q belong to the set of integers, right? That is what they are. So I can take an integer 1 and I can fill in any natural number and I can map it. Okay, yeah, okay, so 1 by n, then 2 by n, so on, so forth. I can go till eternity, sorry, infinity, till infinity. Okay, I will never exhaust this set. I will always be able to map again the same thing, a number from this set to a number in the set of rationals. Okay, and I can't remember exactly. They show some kind of mapping. One by two, 2 by 2 is again one. Then 3 by 2, 4 by 2 is two. Okay, so like in some examples they have shown this kind of mapping. I don't understand this. I just go by this concept. Okay, watch that also if you find. Anyway, coming to the main point now. See, what do we have here? Let's say I have 1.42 and 1.43. Okay, is this the next number, next rational number? No. I can write 1.421. Is this the next one? No. I can still write 1.4201. Can you see? I can introduce any number of zeros between 2 and 1, and I will keep getting a number that is larger than this number but smaller than the preceding number. Like, next I can do is 1.42001. So this is greater than this thing, but smaller than this. So I'll always have this kind of numbers. Also, look closely, these are all rational numbers. They are not irrational. I can write it as 142 by 100. I can write this as 142,001 over 10 to the power 1, 2, 3, 4, 5. Right? So these are rationals. These are all rationals. But also, can I introduce a number in this of the type 1.420100100001? I can introduce this number between what now? Yeah, between this and this. Okay, I can introduce an irrational number, and not just an irrational number. Next thing I'll do is I'll make this 2. Next thing I'll do is I'll make this 3. I can have infinite combinations. Also, these numbers have no limit, no end, they are infinite. So I can put n number of rationals also. See, this was a rational I put between these two, and this black one, this is an irrational I put between these two. And if you clearly observe, we can put in infinite numbers of rationals and irrationals between these two, right? So this is what explains when we say that between 2 points on the real line there are infinite number of rational and irrational numbers, right? This is what it implies. Now look, this irrational, this cannot be, this is no end, it does not terminate, so we don't know when, it is not possible to convert it into a fraction. So it can never be written as a combination of natural numbers or of integers of the form p over q. We can never get a map from the set of natural numbers to the set of irrationals. And this is why, okay, let's write it again here. This is why the set of irrationals, and this was our set of rationals, and this was the set of naturals, right? Now look, this obviously p over q, any number in this set is of the form p over q, where obviously q is not equal to 0, right? So the mapping exists between these two sets. Therefore, the set of rational numbers is countably infinite. However, this set of irrationals, no, we do not have a map. We do not even have, like, in a number. Okay, also, see 1.42 and 1.4201. Yeah, we have gone through this. Okay, so this is 142 by 100, and this is 14201 by, like this. So yeah, mapping, okay, it exists. When we start mapping, taking individually p and q as natural numbers and assigning different values, we will get to this number, we will also get to this number. Okay, so it's not, yeah, like 2 and 8 by 4 in this mapping, we will get repetitions also. But obviously, in a set, repetitions are redundant, they don't mean anything. Okay, so every, like this and this number will be counted only once, will be mapped to just one natural number. Okay, this is a one-to-one mapping. Okay, and now set of irrationals, no, we do not, it's endless. We can, firstly, it cannot be converted into the form p by q, so it cannot be written in the form of natural numbers or integers somehow. Okay, so this set is uncountable. It is infinite, no doubt, but it is uncountable because there is no certain map. Okay, I hope this is clear. And if not, like, I don't think I can explain anything more. This video was not structured, but if I'm missing something, I'll make a part 2 of this. And if you think you're not getting any point in this, or you have any doubt, just ask me. Okay, yeah, I think that will be all.